Hello, welcome to my pipeline integrity video series. My name is Colin Scott. I'm a pipeline integrity engineer based out of Calgary, Alberta, up in Canada. Today's topic is going to be trying to answer the question of how tough is tough enough? There are some times in the integrity business where we're doing a crack assessment and we feel that we've got a tough enough material that we don't necessarily need to worry about a fracture model. Sometimes we think that if we're tough enough, we can get away with using some of the ductile fracture models, for example, ASME B31G or something like that. What we're going to do today is we're going to take a look at the mathematics and try and figure out how tough is tough enough. At what point do we have enough toughness where we can put aside our crack management equations and basically assume that we're going to have a ductile failure that can be modeled appropriately with a metal loss type model. Let's take a look. Those of you that know me know that I work with a model for failure prediction that's of my own development. It's called the gamma exponent model. And here we have the gamma exponent model, or GEM, specifically for surface cracks. You'll see that it looks a lot like the original log secant model that some of you might be familiar with. The key difference is, though, the original log secant model was derived based very strongly mathematically and theoretically on length, which really isn't super appropriate for surface cracks. I've basically redone the derivation and focused a lot more theoretically and mathematically on depth. And this is the equation that I land on. So far, starting from the left-hand side, we have the failure strength divided by the flow strength is equal to 1 minus A over T to the power of the gamma exponent. That A over T is the crack depth to pipe wall thickness ratio. So essentially the 1 minus A over T is a remaining ligament. And then we have a 2 pi arc cos exponential term. Kmat is the toughness. A is the crack depth, and we've got the flow strength in there. Now, the gamma exponent defined for a crack is the minimum of the crack length divided by the radius of the pipe up to a maximum of 1. Now, I've put together a couple of other videos that explain this in a little bit more detail, and they tell you about the fine print. I'm just going to bounce through the fine print very, very quickly for anybody that hasn't seen those other videos before. Please feel free to stop the video and take a look if you're interested in knowing the fine print for this model. So here's my first page of fine print. Stop if you need to. And here's my second page of fine print. Now, if we take a good look at this GEM, this gamma exponent model for surface cracks, we'll see that it basically comes in two parts. The front portion of it is essentially a flow strength model. So that's going to be comparable to something like an ASME B31G model. And then the back half of the model, the arc cos exponential term, that's where we have all the fracture terms. That's the fracture strength model that comes into play. So when we're thinking about under what situations could you really not worry too much about the fracture strength side of the equation, we really do have to look at the right side there that I've got a red bracket around. And we have to say to ourselves, hypothetically speaking, if that whole term was equal to 1, it would basically eliminate itself out of the model. So let's see how that plays out. We'll take the 2 over pi arc cos exponential. Then we've got minus pi material toughness squared all over 10 times the crack depth times the flow strength squared. If we can get that whole term equal to 1, or close to it, that means that essentially that term drops out of the equation and we don't need to worry about it. That means that essentially we have a tough enough material and tough enough conditions that's going to disappear from the equation. And in order to get that arc cos exponential term to be approximately equal to 1, we have to get the exponential term approximately equal to 0. Now, this is really mathematically not super difficult, but I think that if you're like me, you've probably forgotten what the arc cos equation looks like and need a little bit of a reminder. So what I'm going to do is give you a quick little example. So here we have an XY plot. I've just done a simple y equals arc cos x, and that's shown by the blue line. So that's sort of mathematically what we're looking at. Now, hypothetically speaking, if you have a very high toughness material, low yield strength, and you've got a shallow flaw or thin wall, you're going to be very high up to the left on that curve. And if you were to get right up to that 1.57 point, that would cancel out your 2 over pi factor, and that would give you essentially that whole term would disappear. However, if you've got a low toughness material or a high strength material, you've got a very deep flaw and or thick wall pipe, you're going to be a lot lower down on that arc-coast curve. So that's a situation where that whole fracture term is mathematically going to come into play a lot more, and that's a situation where we can't get lazy with our toughness assumptions. We have to have a pretty good idea what we're doing. So let's see what happens next with the mathematics. Now, in order to get to the appropriate point on the curve, we can't just say that we're exactly equal to 1. We have to say that we're getting pretty close to 1. And the way that we do that is to come up with an arbitrarily low value for the exponential term. I've decided to go with 5%. If you want to go a little bit more conservative, you might go 2% or 1%, but this is really just for demonstration. So if we want to get that exponential term down to 5%, we can basically twist the mathematics around and figure out what the critical toughness is in order to get that 5%. Now we play around and we come up with some math. Now in this particular case, we don't know at this point exactly what potential crack depths we might have in our pipe. So what we do is we put in the wall thickness there. The wall thickness is going to be essentially the limiting depth that you would ever have in your pipe. So we put that T in there rather than an A. If you've forgotten what the exponential curve looks like, that's the one here shown by the blue curve. We have x and y equals exponential of x. Now, if you have a high toughness material, low yield strength, and a shallow flaw or thin wall pipe, you're going to be on the left side of that curve. You're going to be very, very low down. And that's what's going to allow you to cancel out your fracture term. However, if you have a low toughness material, high yield strength, and a deep flaw or a thick wall pipe, you're going to be a lot closer to 1 there. And that's going to mean that you're going to be lower on your arc-coast curve, and that's also going to mean that you're going to have a much lower predicted failure strength because that fracture term is really going to come into play. Now, I mentioned that if we want to calculate our critical Sharpie value, we're going to have to play around with our toughness correlations. Now, I use the Wall&J lower bound correlation. There are some pretty important reasons for that. I don't recommend messing around too much with which Sharpie correlations you're using. But it's fairly easy to calculate what is the critical Sharpie value based on the critical toughness that we just calculated in the slide before. So what I've done is I've decided to go through that whole calculation for, I think it's 5 or 6 different wall thickness pipes. Yeah, here we go. So we have 5 different wall thickness pipes. At the top, you see the thickest of the pipes I've selected. It's 9.5 millimeters, and that's shown by the black curve. And then at the bottom, I've got the red curve that's represented by a much thinner wall, 4.8 millimeters in this case. And so the way that you would read this plot is you would take a look at the pipeline that you were interested in. You'd figure out what the yield strength is, the grade, and you'd read that along the x-axis. And then you would take a look at the appropriate curve for the appropriate thickness. Now, if you take a look at that curve and figure out the critical Sharpie value, essentially that's going to tell you the minimum Sharpie value that you have to have in order to not worry about the fracture term in the equation. If you have a Sharpie value that's less than that critical value, then there's the possibility that that fracture part of the equation is going to come into play and you can't disregard it. So let's take a couple of examples. First of all, we'll take a look at a grade B pipe. So that's going to have 240 megapascals of strength. And let's pretend that we're looking at a thicker wall, 9.5 millimeter pipe. Now, if you look at that red dashed circle, that's showing that your critical Sharpie value is about 30 joules. Meaning, if you know that you have more than 30 joules of toughness in the pipe, then essentially the fracture term in the equation is going to disappear and you are okay to do a calculation without specifying exactly what the toughness is because that whole term is going to disappear. Now, this is not to say that you're necessarily going to treat the flaw as a metal loss flaw, but you are going to take into account that that fracture term has disappeared. When you look at the GEM model, the GEM model differentiates between whether you have a crack and whether you have a metal loss flaw, and the change there comes into play. You would use a different gamma exponent if you were to look at metal loss itself. So I'm not recommending doing a metal loss calculation. I'm just demonstrating that under these conditions, the fracture term falls out of the equation. So grade B, 9.5 millimeter pipe, if you've got better than 30 joules worth of toughness, then the fracture term essentially falls out of the equation. Let's look at something at the other end of the spectrum though. So here we have a much higher grade. So this is 600 megapascals, much higher strength material. In this case, we've gone with thinner wall, 4.8 millimeters. From a mathematical perspective, it seems that we need to have at least 60 joules worth of strength in order to have that fracture term disappear out of the equation. And if you think about that, actually makes sense. Because you've got a much higher yield strength material, you have to have an appropriately higher toughness in order to cancel that term out of the mathematics. So here we would say to ourselves, hypothetically speaking, if we had, say, 40 joules of toughness, that would not be enough to ignore the fracture term. We would have to keep that fracture term in our mathematics as we do our various assessments. Hopefully that makes a little bit of sense. In summary, if you're looking at a more brittle failure, that's going to be characterized by a low toughness material, a higher yield strength material, and a thicker wall. And if you have a more ductile type failure, that's going to be represented by high toughness, low yield strength, and a thinner wall. So that's kind of it in a nutshell. The plot that I gave you is fairly simplistic. Hopefully it demonstrates the important things to think about. And hopefully it will get you thinking about how you might be able to simplify your own pipeline integrity programs in the event that you have a higher toughness or lower strength pipe. It might make your calculations quite a little bit easier in certain situations. So if you're interested in the pipeline integrity video series, I do have several other videos that might be interest of you. The first one is called Pipeline Integrity Things That Make Me Go, parts 1 to 6. That's essentially a critique of the original Battelle NG18 equations. I think if you take a good look at the mathematics behind those models, there are some fundamental problems that really need to be fixed by industry. They seem to have a bit of a length and depth snafu that results in some really, really wonky mathematics and very expensive programs for a lot of the pipeline operators. I've also got several videos where I look at how I've validated my gamma exponent model. I've demonstrated that it can be derived into a failure assessment diagram type approach, and I show that it can be used to look at leak rupture boundaries. I do also have some real publications, one through NACE, two through ASME. Help yourself to finding those. If you're a math nerd and would like to learn a little bit more about how the GEM was derived, take a look at that bottom paper, ASME Journal of Pressure Vessel Technology. That gives you a lot of the mathematics behind the GEM derivation. If you've made it this far, thank you very much for your attention. I appreciate it. I hope that I've given you a few things to think about, and if possible, it might help you streamline some of your own pipeline integrity assessments quite a bit. But it really does come down to having a pretty good understanding of how your toughness and your yield strength and your wall thickness all kind of come into play mathematically. So hopefully that makes a little bit of sense. Thanks very much for your time. Bye for now.